Today we're going to be talking about Buhlmann and Buhlmann-Straubb credibility. The previous groups went over Buhlmann credibility applied to specific instances, and we're going to be teaching more general equations that'll work in any situation. Since these models are topics of credibility theory, I'd like to give a brief overview of what credibility theory is, just to remind us. Credibility theory is a set of quantitative tools that allows insurers to adjust future premiums based on policyholders' past experience. So insurers would like their premiums to be correctly proportional to specific policyholders' risks. So for instance, if a policyholder is less risky than the average policyholder, the insurer might want to reward that policyholder with a smaller premium. And if the policyholder is more risky, the insurer will want to raise the premium so they don't lose any money off that person. The only way that insurer can tell if a policyholder's risk is different than the average is based on their past observed data for that specific policyholder. So it becomes really important to know how much of the difference in experience of a given policyholder is due to random variation in the underlying claims experience, and how much is due to the fact that the policyholder really does have a better or worse risk than the average policyholder. So credibility theory is the method we use to answer that question. The credibility of a person's data, if it's really credible, then their past data, we can believe it to represent their risk. But if it's not credible, we should go with what we assumed from the beginning about the average policyholder. So just to get us thinking about how credibility works, we have a brief example. It says an insurance company has two types of insurance. High-risk insurance have a mean loss of 2,000 with a standard deviation of 1, and low-risk insurance have a mean loss of 1,000 with a standard deviation of 1. Qualitatively speaking, how many claims does an insurer need to file before you can determine whether or not he's in the high-risk group? The answer is going to be very few. So if we just think about this for a second, say an insured has a claim of 1,998. Because the means are so separated from each other and the standard deviations are really small, just based on one claim, we can tell that that person is going to be in the high-risk group. His past data is going to be really credible. If we look at another situation, where the high-risk insureds have a mean loss of 1,002 with a standard deviation of 500, and the low-risk insureds have a mean loss of 1,000 with a standard deviation also of 500. In this situation, how many claims does an insured need to file before you can determine whether or not he's in the high-risk group? We would need many. So to just think of an example, if we got a claim from a policyholder of 998, the means are really close together and they have a huge variance. So we wouldn't be able to tell based on that claim which group they're in. We'd need to have a lot of data for each policyholder before we could decide which group they're actually in. And so in this case, the credibility of past loss experience would be pretty low generally. Okay, now we're going to talk about Fieldmans K, which is going to be a really important variable for use in Buhlmann and Buhlmann-Straubb models. So we start with the loss amount x, which depends on parameter theta. And so to calculate K, we first need to find the EPV and the VHM. So the EPV, which stands for expected process variance, and it's also sometimes called V, is equal to the expectation of the variance of x given theta. And then the VHM, which stands for the variance of the hypothetical mean, which is also sometimes called A, equals the variance of the expectation of x given theta. And so it's really easy to remember which is which. This is the expected process variance, and you do the expectation of the variance. And same here, the variance of the mean, and you do the variance of the expectation. So the names like help you figure out the formulas really easily. And then K just equals V over A, or EPV over VHM. And just another note, the variance of x we know is the expectation of the variance of x given theta plus the variance of the expectation of x given theta, which is just V plus A. So if you ever need to find the variance and you do know V and A, you can find it really quickly by adding them together.
All right, so going back to the first group of problems that Zach talked about, we have here an insurance company has two types of insureds. High-risk insureds have a mean loss of 2,000 with a standard deviation of 1, and low-risk insureds have a mean loss of 1,000 with a standard deviation of 1. What's different is we're trying to calculate Buhlmann's K. So we know that the variance of x conditioned on the group is 1. And to find the EPV, or the expected process variance, we need the expectation of the variance of x conditioned on the group. So that is also equal to 1. So what we have is V, which is equal to EPV, is equal to 1. The next thing we want to find is the expected value of x conditioned on the group. And we need this for calculating the VHM. Obviously, in the high insurance group, we have 2,000. And for the low risk, we have 1,000.
Can't say higher interest.
So the next thing that we want to know is the variance of the expectation of x conditioned on the group, which will give us the VHM. And this is whenever you're trying to find a variance of a random variable that can take on two values, the formula is just 2,000 minus 1,000 squared times the probability of being in the high risk group times the probability of being in the low risk group. And that will give us 250,000. Can you stop real quick? Okay. Now that we have both the EPV and VHM, we can calculate Buhlmann's K. K is just the EPV over VHM, which in this case is just 1 over 250,000. So here we can see that K is very tiny. And so going off what Zach said earlier, we know that K is tiny, and we also know that in this example, it takes very few attempts, very few new data points to determine which group someone is, if they're in the high insured or high risk or low risk group. Now let's take a look at the second problem. Where the mean of loss of the high risk is 1,002 with a standard deviation of 500. And here is low risk is 1,000 with a standard deviation of 500. So going through all the calculations real quickly, we have the EPV is equal to 500 squared is equal to 250,000. The VHM is equal to 1,002 minus 1,000 squared times the probability of being the high risk group times the probability of being in the low risk group, and that is equal to 1. So here, Fieldmans K is just the opposite, 250,000 over 1, and so here it is large. And previously, we also know from this example that it would take a lot of new data to figure out which group of insureds you're in. And so our conclusion is that if you have a tiny k, it takes very few new data to figure out which group you're in, and vice versa for a situation like this. So when k is large, we are going to put a lot of weight on our prior assumptions, and when k is small, we're going to put a lot of weight on our new data. And that is it. So this idea gives us the credibility formula, 1 minus z times mu plus z times x bar. Mu sort of relates to the prior distribution or the original data, and x bar relates to the new data or what we get out of the problem. So I want to put weight 1 minus z on the manual premium and weight z on my experience. And so that's where the k kind of fits into the z. Just a little note. When k is large, z is small. So this formula can also be written as mu plus z x bar minus mu. And just going over formulas you guys already know, z is equal to n over n plus k. N is the number of data points. K is just V over A, or EPV over VHM. And mu is just the manual premium. And the way that we calculate this is using a double expectation. It's the expected value of x conditioned on beta. So when we solve for k, we just want to keep in mind that when k is large, we put a lot of weight on the prior assumptions right here, and when k is small, we put a lot of weight on x bar, which is our new data.
Alright guys, so I'm doing this Buhlmann credibility example where we are given a two set of information. The first one is saying that the number of claims made by an individual insured in a year has a Poisson distribution with mean lambda. And the second information tells us that the prior distribution for lambda is a gamma distribution with parameters alpha and theta equals to 1.2. So what this question asks us to do is based on a 2 years worth of data where it says we have 3 claims observed in year 1 and 0 claims observed in year 2. We are trying to use the Buhlmann credibility to estimate the number of claims in year 3. Alright, so let's set up some information given. So I'm going to set this number of claims as n. And then from the first information here, we know that n given lambda is a Poisson distribution with mean equals to lambda. Alright, and then from the second information, we know that lambda is basically a gamma distribution with alpha equals to 1 and theta equals to 1.2. So we are going to use those 3 information to work this problem. So the first part we're going to do is we're going to calculate the EPV, which is basically the V. And it is from what Zach and Kevin has discussed, it's basically the expected value of your variance of your n given lambda. And then because we know that a Poisson distribution with mean of lambda has a variance that also equals to lambda, so we can set this equals to E of lambda. And because lambda is a gamma distribution with alpha and theta such as that, and you can look it up on your C table, and it's going to keep the mean of a gamma distribution is alpha times theta, so we will end up with 1.2. Alright, and then on the second part we need to calculate the VHM or the A. So in this case, A is the variance of the expected value of our n given lambda. And since we know that n given lambda is Poisson distribution with mean lambda, we know the expected value is that. So again, we're going to have a variance of lambda, which gonna gives and if you look at the tables, you're gonna get alpha times theta squared, which gonna gives us 1.44. So again, after you got your V and A, you will be able to calculate your K, which is just V over A, and that's gonna gives you 1.2 over 1.44, and that's just gonna end up 1 over 1.2. Alright, again, since we already talked about that we have 2 years worth of data, year 1 and year 2. So on this Buhlmann credibility, that's going to be our n. So we know that our n is equals to 2 with observation of 3 claims in year 1 and 0 claims in year 2. So if we want to calculate our x bar, it's going to be simple. It will be 3 claims from year 1 plus 0 claim in year 2 divided by 2, and you will end up with 1.5. So, and then we already got our K, we know what our N is, so we can calculate our credibility factor, which is just Z, and that's formula for that is N over N plus K. So you have your N as 2, so 2 over 2 plus 1 over 1.2, and so we're going to leave it just like that for now, and then after that we need to calculate our mu, or our manual premium. You can call it either way, and that's just gonna be your expected value of N. Alright, so from the expected value formula, as you know that the expected value of N is basically the expected value of the expected value of N given your lambda. And that's, since we know that our N given lambda has a distribution of Poisson, we know that it's just gonna leaves us with e to the lambda, and that's like what we have calculated earlier. E to the lambda is 1.2. And then I'm gonna need some switch. Are you pausing this? Alright, so we have our mu, or our manual premium. We have our Z as our credibility factor. So to estimate the number of claims in year 3, it's basically equals to the credibility premium. And the formula for that is the mu plus Z of X bar minus mu. So just plugging in all the numbers that I have calculated earlier, we know that our mu is equals to 1.2 plus our Z, which is that, 2 over 2 plus 1 over 1.2. Multiply that by the difference between the X bar, which is 1.5, minus our mu again, which is 1.2. So if you calculate this whole thing, you will end up with 1.41. So in the end, based on your prior experience of 3 claims in year 1 and 0 claims in year 2, using the Buhlmann credibility method, you will be able to estimate the number of claims in year 3, which is equal to 1.41.
This example is very similar to the one that Alex just did, but the difference is that we'll be calculating Buhlmann-Straubb instead of Buhlmann credibility. And the only difference between those two is the way you compute your N. And in Buhlmann credibility, your N is a number of periods, whereas in Buhlmann-Straubb, N is a number of exposures. So it's very similar to the previous problem. Like our parameter is, our number of claims are distributed Poisson, and then our parameters is distributed gamma. So our question is, the number of claims incurred in a month by any insured has a Poisson distribution with mean lambda. Claim frequencies of different insureds are independent. The prior distribution is gamma with probability density function, this. And I guess we can look at this closely and figure out what our theta is. Our theta is going to be 1 over 100, and our alpha equals 6. We're given this observed data, and we want to determine the Buhlmann-Straubb credibility estimate of the number of claims in month 4. So like before, we're going to have to calculate a bunch of values and plug it into a formula. So for this, first we will calculate EPV, or known as V, and this is the expected value of the variance of N given lambda. And also, just to note, I'm going to refer to N, and that's just the number of claims. Okay. And the variance of N given lambda is just going to be lambda, because the variance of a Poisson is lambda. So this is going to be the expected value of lambda, which in our case is distributed gamma, and the expected value of the gamma distribution is beta times alpha. In this case, it's 6 over 100. So next, calculate the VHM, or better known as A, and this is the variance of the expectation of n given lambda. And the expectation of n given lambda is, again, lambda because it's a Poisson distribution, so it's the variance of lambda, and lambda is distributed gamma, so the variance of a gamma distribution is beta squared times alpha, and in our case, it's 100 squared. Okay, next we will calculate K, and this is referred to as Buhlmans K, and it equals V over A, and in our case, it's just 6 over 100 over 6 over 100 squared, and it equals 100. Our number of claims is just the number, our n is the number of exposures, and in this case it's 100 plus 150 plus 200, which equals 450. So, and our x bar is the average number of claims per insured, which equals 6 plus 8 plus 11 over the number of insured, which we just calculated as 450. And this equals 25 over 450. Okay, I think we need to pause. Okay, now we need to calculate our mu, or it's also known as the manual premium. And this is just the expected value, the double expectation of n given lambda. And in our case, lambda is Poisson, so it's the expected value of lambda, which is 0.06. And our z, which is n over n plus k, equals, n is 450, and k is 100. So this equals 450 over 550. Okay, now we can calculate the Buhlmann credibility, which is mu plus x bar minus mu. And we already have all these values, so I'm just going to plug them in. 0 plus 0.6. And your x bar is and this equals. Okay, now to determine the number of claims in month 4, you just multiply your Buhlmann credibility by the number of insureds in month 4. So in this case, it's just 300 times 31 over 450, which equals 550, which equals 186 over 11. Okay, I don't know how to do a closing, sorry.